Hello, everyone. My name is Ryan Schul. Welcome to my channel. This is all about advanced analytics. Okay, so in the narrative today, I want to focus on using a graph-based technique to find fraud rings, and we are going to leverage community detection. Okay, so we're going to try to determine how these communities of fraud rings, I believe that's what they're called, how they operate, and the kind of like the fingerprints that they leave or the traces that they leave behind, and use this to figure out where fraud is occurring. Okay, so now I don't work for a credit card company. I don't work for a bank, so I don't have access to this data, but I'm going to show you if you work either on some type of risk management team or anti-fraud, AML, anti-money laundering would be highly similar to this. If you work on one of these teams or managing one of these teams, this would be a very good approach to detecting fraud in some pretty complex scenarios where it isn't necessarily obvious. Okay. So again, I'm going to go ahead and create the data because I don't have this data. I don't work for these companies. And even if I did, I can't take the data and record a video and post it on YouTube. That would be highly, what's the word? Highly unscrupulous, I guess, right? I can't post credit card transaction data, but I'm going to create data that is very realistic, and you could go ahead and substitute your actual data for the data that I'm going to create, because again, I don't have this, right? And I shouldn't have this either. So we have the number of cards over here, number of merchants, transactions, just some very, very basic information here. Probably you don't need a ton and ton of information, right? You would need these three to start with. You would have a couple other types of things, the amount of the transaction, the probably the device ID, IP address, if it's coming from maybe a phone, right? Because you can have Apple Pay. I'm getting behind on the times. I don't even know how some of these things work. I know barely how Zelle works. There's there's another one, Venmo. I know a little bit about that. I should really do some more research to get up to speed. But you can pay with your phone. I know that for a fact. I've seen people do it. Transaction IDs, the time of the day of the week, the hours. So if there's fraud occurring, like maybe between 10 o'clock and 2 a.m., that would be something that we would be interested in detecting, right? And focus more on these transactions and shine a light on these that are occurring at this time of day, right? If there's more fraud, maybe on Fridays, maybe on Saturdays or Sundays, I'd like to be aware of that, right? So these are some types of things that we can kind of like tease out from the data and try to extrapolate and try to explore a little bit more. But again, we do need these basic types of information to start the analysis. So I create a list over here in many, many, many of my videos, probably several hundred videos, and doing exactly the same thing over and over. There's just different applications, right? So create a list object. There's four primary types of objects in Python, and it might be a couple of more. I don't use too much more than four. This is the dictionary. List I use all the time. Tuple, which I hardly use, but sometimes it is useful, and a data frame. So we'll see a couple examples of lists and data frames. Here's the list right here. I'm appending all the data into this list and then returning a pandas data frame down here. So I've got the basic information set up. I have the transaction ID, the time of the day, like time and second over here, card ID, merchant ID, the amount, that's pretty important, device ID, and IP address. Then we're going to go ahead and create buckets, okay, to get time window. Again, like I'm interested in knowing the time of day when these transactions are typically occurring. Is it just all over the place and there's no pattern whatsoever? Or is it primarily early in the morning, afternoon, evening? I would say mostly maybe overnight, but again, I don't know. That's what we have to figure out. That's why we're doing this analysis. So that is the setup right there, and we're taking the overall counts of transactions, the summing of the amounts, the first and last transaction, and again, device ID. So a credit card, I wouldn't call that a device per se, but if you have a phone and you're paying on that, that will have a unique IP address. I can guarantee you that for any phone, for any desktop, laptop, they all have their own unique IP addresses. I think even printers and even servers have their own unique IP address, right? That's the, I think 16-digit number that you see. 1, 2, 4, 5, 6, 7, 8. Let me see if I can find one. You've probably seen this before anyways. let's see. So I don't think a credit card will have an IP address in the traditional sense of the word, but it's going to have a unique card number, and that's for sure, right? So that would be just different means for paying. Okay, so this is kind of what it looks like. You have um, three numbers, then a dot, then up to three numbers, then a dot, then up to three, and then up to three, right? So there's lots of combinations. Here's one over here. What do they say? Leading bits, size, and number of networks, number of addresses per network. Okay, so it can go from 0000 up to this number right here. So there's lots and lots and lots of combinations for IP addresses. Okay, so I digress. We're going off on a tangent there. So now we have to go ahead and create the card-to-card graph. So we want to know, is the same type of card being used maybe by different people? That would be highly unusual, right? Unless it's maybe a husband and wife sharing a card. But if you have sort of like a large network, maybe a dozen different people using one card, that would be highly unusual. So we want to go ahead and create connections and nodes and look at the strength between the nodes to try to understand how are all these different data points connected, right? Are multiple people using one card? Is one person using multiple cards? That's totally fine. If a dozen people are using one single card and they're passing it off and handing it off to different people, that would be very unusual, right? So this kind of network analysis is going to help us figure this out. If you just want a very basic example of this, not even maybe cards is a little bit abstract and you're not ready for that. Imagine all your friends on Facebook or your professional connections on LinkedIn, right? You will have your connections will have other connections, and those other connections will have a whole bunch of other connections, right? So it's a huge network out there, and using this network analysis technique, we can go ahead and see how everybody is connected to everybody else. There's a concept called 6 degrees of separation from Kevin Bacon, or maybe 7. Somebody came up with this a while back. It was kind of interesting. And it was basically everybody's connected to everybody else within 6 or 7 degrees. What was that thing? I forgot. 7 degrees? I think this is it, 7 degrees of separation. Oh, it's 6 degrees, whatever. I heard about this a long time ago. And apparently, everybody is connected to everybody else. And somehow within 6 degrees, everybody's connected to Kevin Bacon. Here's a good image over here. Okay, so that's kind of what we're trying to do with this network graph. Okay, let me put that away. So that's the basis for the analysis here. We have to look at the nodes and then the connections between all the nodes, and then look at the cards and which merchants are using which cards. And we're going to try to take all this information that's somewhat complicated and just boil it down to a very simplified solution, and then throw that into a network graph. I set up the network graph right here. You can see that. And we're looking for all possible combinations. So we're going to go through all the different rows in this network and all the different columns. And this is what the I and the J is for, right? So for all I in range length cards list, and for all J in range I plus 1 of the cards list, we're looping again through every possible combination of rows and columns and looking how everything holistically is combined. So it's a kind of a simple type of problem. It's kind of complex at the same time, but using this technique, this network graph analysis tool, it's not that complicated actually, and we can break it down into bite-sized chunks and solve the problem pretty straightforward in a pretty straightforward fashion. And by the way, whenever you're dealing with any kind of complex problem, you always want to break it down into the smaller chunks until you can solve the problem, right? So I've worked on some complex problems over the course of my career. I was on Wall Street for about 22 years, and sometimes my boss would come up with extremely complicated problems. So myself, sometimes it was just me, sometimes it was me and a small team. A lot of the times it was just me. You just break it down into smaller and smaller and smaller and smaller granular chunks, solve each one, and then rebuild the process from the smaller problems that you solved, right? You solve 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever. And now the whole problem is solved. Then you just have to rebuild it and you're done, okay? So that's what we're doing. We're breaking something that's kind of complex down into something that's fairly straightforward, looking at all the combinations of merchants and cards that were used at each merchant site, I guess. each merchant address or location, whatever you want to call it. And then we will have the size of the transaction, the density of the combinations of all these different transactions, the average weight of these transactions, triangles. So we're looking at these relationships between different transactions, maybe different merchants, transitivity, merchant entropy. So this entropy is something that's getting more and more, what's the word? Kind of like uh, disintegrating or disappearing or dissipating. It's more dissipation over time, right? Like if there's a big gust of wind, the wind can be intense and very focused for a short period of time, and that kind of dissipates. That's one example of entropy. I'll let you Google that and see what you come up with. There's all cases for entropy, but we're trying to minimize the entropy and the dissipation and understand the concentration of these relationships. So the mean amount of the transaction, average transactions per card, that's important too. If there's one or two big ones, that could be considered fraud, but not necessarily. If there's a whole bunch of smaller, similar transactions, that could be considered fraud, but not necessarily, right? That's why we have to do this graph analysis. So like when you put money into a bank, if it's over $10,000, the bank is going to ask some questions and say, well, what's the source of this money? Where is it coming from? Because they don't want to enable money laundering, and they don't want to take $1 million from somebody and then push that into the monetary system and create money laundering, right? So you have dirty money from some kind of drug transaction, and then the bank washes it and it becomes clean. So they have a limit, at least my bank does. You can't put in more than 10,000 at a time without declaring where the source of the money is. So a money laundering ring can make a whole bunch of deposits for $9,900, and it would come under the threshold, and it would look clean to the bank. It would look fine to the bank, but that could still be money laundering, right? So a lot of very similar repeatable transactions that are essentially the same thing, but under the $10,000 threshold, that could be considered some type of fraud, right? So we have to be aware of that. Shared device pairing, IP address pairs, right? We're looking out for that in transactions per day. So we're taking all of this, ranking all of these, right? So we have the feature positives based on density, transitivity, average weighting of the connections between these different nodes in the network graph, transactions per day, shared devices, and shared IP pairs. And then entropy, again, we want to try to minimize entropy. We do this a lot in the data science world. If you have more and more entropy, the model isn't learning very well, and it's not able to learn and make predictions into the future about what's going to happen next on data that it hasn't seen yet, right? So if the entropy is high, the model won't transfer well to unseen data points because it hasn't learned very well the historical data points that you sent into it, right? That you fed into it. But if the entropy is minimized, then the model is learning well, and then you have a higher degree of confidence that the model can make predictions on unforeseen data that it hasn't seen yet, right? So if it's seen the data, it knows exactly what to do. It's going to memorize that, but you want it to make accurate future predictions on unseen data. That's the whole point of that exercise, right? So Control Enter to run this, and we will get our data frame with everything I just described. I'm going to look at the top 10 records right here. That's what the head 10 is for. This is the community data frame right here. Okay, so we have the community ID, size, density, average weights, triangles, transitivity, merchant entropy, average transactions per card, shared device pairs, IP addresses, transactions per day, and ring score. So we're actually going to assign a score to these potential fraud rings. So when I look at this, I'll show you how to interpret this in just 1 second here. We have different communities. We have a community 5, 0, 2. These are like different clusters. So a community can be one person. It can be multiple different people. Right here you see the size of the community is 9 right here. So it's multiple people, or maybe multiple small businesses or something like that. Hasn't really been defined, but there's multiple items in this category. And the density of 1.0 pretty much guarantees this is a click, and all these cards are connected to every other card. So this is highly suspicious. This is almost a guaranteed fraud ring right here, okay? Anything with a density of 1.0 is going to be highly fraudulent, right? The higher, the more likely you are to have fraud. These down here are lower numbers, so much less likely to be fraud. The average weights are pretty high over here. So again, this is indicative of fraud. And anything 8 to 9 is pretty high. These are shared merchants and overlapping windows and shared device IPs, right? So it's almost like somebody is using a phone, then they give the phone with Apple Pay on it to another person to use it, and then that person does a handoff to another person using the same phone, the same IP address, but a totally different person, right? So these are very suspicious. Anything that's over 8 is suspicious. These are lower, right? So I'm not worried about these. But these top 3, you have density 1.0, 1.0, 1.0. That's suspicious. These 3 are suspicious. Okay. Low entropy is suspicious. So merchant entropy is 1.3, 1.3, 1.3. So those are all suspicious. It's a little bit higher, so that's not too bad. Average tax per card, 18 is very high because the ring basically transacts in a short burst of windows, right? So as a velocity spike. So the anything around 18 or so is going to be almost guaranteed fraud. What else? Shared pairs of devices or shared IP addresses. These are all high numbers right here, right? High, high, high. So high is bad, high is bad, high is bad. These numbers down here are lower, and lots of transactions per day. So these guys are doing a lot of transactions, handing off the cards or the iPhone or whatever it is. I think you can even use your Apple Watch now to make payments. My son just got an Apple Watch a couple of days ago. He loves the thing. He's enamored with it. I think you can probably pay with the Apple Watch. I don't know. But again, this is going to have a unique IP address, and you have to be able to have a device that you can share easily with people and have high velocity or high frequency transactions in a short period of time. So you have 81 charges on this phone or credit card or whatever it is. That's a lot of transactions in one day. Like I don't have 81 per month. So that's very suspicious, right? So these 3 records right here, these 3 are guaranteed fraud, right? That's what we have to focus on. So if you're in risk management, AML, anti-fraud, maybe you work for the FBI, maybe some bank, maybe some credit card institution, this is where you want to spend all of your time right here. And I'm actually assigning a ranking. So the higher the worse. This is the number 1 worst fraud evidence in this data frame. This is pretty high. This is pretty high. These are all negative. So we can just leave these people alone, right? And we're looking at the ring score. So we're getting the score, assigning a ranking, right? Feature ranking for these fraud rings. Ascending equals false. So this is in descending order. I don't even think there's such thing as descending. Ascending is either true or false. If I do this again, you'll see the lower numbers at the top. But this isn't what we want, right? We want to focus on the descending records because we just saw that the first 3 were fraudulent fraud rings, right? Just showing you how this thing works really quick here. And I have my notes down here that just confirms everything that we just saw. So this is no fraud over here whatsoever, right? So these guys are totally fine. And I think we only have 6 records here, so kind of a smaller data set. But again, we aggregated and did some commingling of data up at the top, right? So let me go back to where we were before. So we only have 6 records. And I saw the same fraud. They were pushed down to the bottom because we were going in ascending order. Now we're going in descending order, right? We get that from this right here. I have to look that up. I don't think there's anything called descending in the pandas world. Okay, so we have the top 3 fraud, and then these other 3 guys down here are totally fine. We leave them alone. We focus all our efforts on these 3 fraud rings. Okay, there's my notes. And because this is a network graph analysis, I'm going to create a visual representation of everything I just described above. You can see community 5 is the number 1 worst fraud ring. This has a density of 1.0, average weight of 9.5, entropy of 1.38. So that's pretty low. Remember, low is bad. Normally in the data science world, low is good, but in this case, low is bad. Okay, so we have to remember the frame of reference that we're operating in. And again, I'm assigning rankings to the ring score. So this is the number 1 worst, this is number 2, and this is number 3. Everything else is fine. And because this is a PyVis network graph, this is dynamic interactive. You can zoom in, zoom out. but we already know like these guys are fine. We just have to focus on 5, 2, and 3. I think that's what it was. 5, 0, and 2. Okay, and leave these guys alone. So these are fine. And we know where we have to put the efforts. Okay, so fraud rings are tightly knit organizations. If a card hits a merchant with the same device and same IP address window, and so this card 8 and B does not equal C, they look similar, and you typically see C with A transactions. We're looking for things that jump out from the crowd, right? So these things can be extremely complicated, but using this network graph technique, we can tease out the subtle differences here in the data and bubble up the items that are the most pressing, the most troublesome, and causing the most destruction, right, in this system, right? Because we can see these 3 fraud rings are very, very, very destructive, and they're getting a lot of merchandise basically for free, right? That's what's going on here. So that's it, guys. I'm going to save this code for you. I will share that when I share the video. I'll drop that a little bit later today. Got a couple things I got to do before that to head off to church here right now. But yes, you will have everything you need. I'll post all this code, post a video with the code a little bit later today, and you can copy and paste that into your own Jupyter Notebook environment, and you have everything you need to run this analysis for yourself. So that's it, guys. Thank you so much for the time today. Appreciate it. Thanks for sticking with me to the end here. And as always, I'm going to wrap it up right here, but I'll see you guys next video, okay? Take care for now. Bye.